This is question 6 from last year's exam. So it's an exam question. It's a good indication of some of the things you can get asked. And we will go through question 9 together on Friday. I'll encourage you to have a go at question 9 tonight, see how far you get, see where you get stuck, and we'll go through a solution together on Friday. Okay, so we've got an oyster farm in South Australia, and we've got mean and standard deviation, so it's going to be a fairly stock standard normal distribution question to begin with. So for our first part, I've got 0.595. Everyone concur?
Yeah.
Very good. Okay, for the second part, I got 0.305. Everyone okay with that? Excellent. So the tricky part is here, where we get to part 2. We have exactly half of the luxury-sized oysters from this farm weigh more than K. So let's think about this distribution of oysters, and we have 30.5% of them are luxury-sized. 30.5% are luxury. That's what the calculation we performed in B. Now we're told half of them, what are we told? Half of them weigh more than K, find K. So half of 30.5 is going to be, what did I write down? 15.26, because I used the 4 significant figures. So halfway in there is 0.1526. Sorry, that's the probability of that, 0.1526, or 15.26%. So you can think of that as luxury oysters are 30.5%, but half of them are more than K. So half of 30.5%, I use 0.1526. I use the 4 figures to maintain a bit more accuracy. Okay, and so then it says, find the value of K for which half of the luxury oysters are larger than. Okay, so that's where we're going. Probability of X being larger than K is 0.1526, inverse normal distribution calculation. Okay, so for that one, I got 87.7. All right. 87.7. So yeah, I think I've justified enough of that there for that one. Okay, very good. Let's move on then. And now, this is how the normal distribution calculations will go. They'll either just do a few straightforward normal calculations, and then they'll either look at it as a sum of a number of calculations or an average. So in the next part we have oysters are sold as a dozen, and they're sold to Australian and European restaurants. Each of the 12 oysters in a package is randomly selected. Okay, so there's this, it's just going by that mean and standard deviation. When sold in European restaurants, it's labelled as having a net weight of 1 kilo or 1,000 grams. So with these stats questions, what you'll notice is they can be a bit overwhelming with text. All right, and so our trial is to go through and filter out what's the important information. So they're guiding you a fair bit. Consider S12, state the mean and standard deviation of S12. So that one's pretty okay. I got 987.6 for the mean of S12, and for the standard deviation of S12, I have 18.36. Everybody okay with that? Okay, and then from there, in part 2, determine the proportion of packages of 12 oysters that have a net weight of less than 1 kilo. So we're talking about the variable S12, and we're saying what's the probability of it being less than 1 kilo? Now be careful here with units, because the units we're dealing with here are grams, and they say 1 kilo, so we need to put 1 kilo as grams, or when we put this information in our calculator, put that in kilograms. Doesn't matter as long as we're using the same unit across all of those. This is the normal calculation we're performing now. Okay, using this mean and this standard deviation. And I performed that and I got 0.75. Okay, so the probability of the sum of 12 oysters being less than a kilo, 0.75. Okay, did people get up to this part? Yeah, absolutely. So for this one, I'm going into normal distribution. I've got a lower boundary, an upper boundary, a standard deviation, and a mean. My lower boundary is minus infinity. My upper boundary is 1,000. So I'm talking about between minus infinity and 1,000. And I'm using this standard deviation because our variable is S12. And I'm using that mean as well because our variable is S12. So you put that information in, and that's how I'm generating the answer 0.75. And so what this means is 75% of oyster dozens are under a kilo. and we're selling them to Europe saying that it weighs more than a kilo, or at least a kilo, that's horrendous. So that's the next part. Comment on. You know, we're sending them to Europe. Is it a good idea? Is it appropriate? So,
sorry, did you just go over the mean and the standard deviation, please? How'd you get them?
Yeah, very good. Yeah, for sure. Yep. So mean of S12. So like you can think of it as the mean of Sn is equal to n times the mean of x. Okay, straight out our notebook. And the standard deviation of Sn is equal to the square root of n times the standard deviation of x. So that's how I'm generating both.
Yeah, thank you.
Yep. So in the second part, so we've got 2 marks, one for saying yes or no, and then the other one for providing a justification. So is it appropriate? No, it's not appropriate. Why? Well, because based on this calculation here, 75% of our dozen oysters are below 1 kilo. So it's definitely not appropriate to claim that our dozens are at least a kilo.
Yeah, this is just a scam.
Okay, but we've got some new farming techniques, and look at that big fat paragraph of text there. Okay, so prime example of what stats question in the exam. So the mean weight of individual oysters was originally 82.3, but we've got a new farming technique. We're going to put some steroids in there, make them grow a bit bigger. And so now we have, and so read through it all, okay? The farming is a new farming method. A sample of 100 oysters, so that's useful. N is 100. Produced using this new farming method is randomly selected. The mean weight of the sample. Okay, so make sure we're careful about the language. So the mean weight of the sample, the value of x was 89.1. Using the sample data, construct a confidence interval and assume the standard deviation remains the same. So standard deviation was 5.3 initially. So now we're doing a confidence interval calculation. You could write it out manually. It'd be a waste of ink and a waste of time. I would jump straight to your calculator and input this information to produce the 95% confidence interval. So I can walk you through those steps again. We're in statistics. We're going interval Z, and then first sample. And then we're inputting confidence level, the standard deviation, 5.3, the mean, okay, the mean of the sample, 89.1, and the sample size, N, is 100. And the confidence interval I got is 88.26 is less than the mean, is less than 90.33. Okay, to round to 3 significant figures, I've told you guys we're going to round the lower end down and the upper boundary up, with the caveat to guarantee that level of confidence. Okay, that's 88.2 is less than the mean, is less than 90.4 to guarantee 95% confidence.
I don't know. Wait, why is that?
Mr. Ross, I've got a different values.
Yeah. I might not put it in right when I did it just here. So 95% confidence, standard deviation 5.3. I've got 88.26 and 90.33.
80.
Is it 8?
I've got 88.06.
Oh, I used 89.3, not 89.1. I did it twice. So I've got 88.06.
Yeah.
Yeah.
And 90.13. 90.13. Yep. So 90.1 and 88.8. Okay, to guarantee 95% confidence.
Doesn't that mean that you make it so it's 90.2?
And yes, round that. Correct, round that up. Am I missing anything else? Okay, cool. So we'll move on. Does the confidence interval suggest the new farming method has increased the mean weight of oysters? Okay, so from this confidence interval, the lowest the true mean of the population could possibly be is 88 grams. Okay, what was the historical mean? 82.3. So let's answer the question. Does the confidence interval method show that it's increased the weight? Yes, it does. Okay, yes, it does, because this confidence interval is completely above the historical mean. So another way you could word that is the lowest the possible mean could be is 88 grams In the past, this was 82.3 grams using the old method. Okay. Cool. So then, after introducing the new farming method, the farm makes the following claim with 95% confidence. No more than 0.2% of our packages of 12 oysters will have a net weight that is less than 1 kilogram. Okay, using your answer part D, provide calculations that support this claim. So what we're checking this calculation again. A dozen oysters being less than a kilo, how many boxes of a dozen oysters are less than a kilo? Okay, but what's changed? The mean. Okay, the mean of oysters. So that means we need to perform the calculation again. And when I'm doing this, guys, I'm going straight from my calculator. I'm in NCD. I've got my lower boundary is minus infinity. My upper boundary is 1,000, and I'm going standard deviation. That is n square root of n times the standard deviation of the thing. So I'm putting that straight in there, so I don't need to perform it separately and then input it again. Thinking of time, ways that we can save time, especially for this one. N12, yep, so 12 times the new mean. Which mean are we going to use? This is the trick here, okay? We may be, can we use the mean of the sample, 89.1? Okay, should we use that or should we use something else?
Something else.
You should do something else, yeah. So it's sort of, I'm hinting at it. What else could we use? We're thinking about this question. We want to guarantee with 95% confidence.
Would you use the lower?
Correct. If we use the lower end of our confidence interval, this is the lowest it could possibly be, and so that accounts for the worst case scenario. In the worst case scenario, this is the new mean. Okay, so let's do that. 12 times 88 point. I'm going to go with the 4 significant figures just to save a few, increase our accuracy. So now we're doing that calculation again. Distribution normal, NCD. I've written it all out. Square root 12, so 5.3 times square root 12, write it out like that.
Can you just put that in when you're sort of explaining the NCD? Just write it in like that.
Yep, that's how I'm doing it, yeah. So, and that is, I've got 0.001029. So that's, 1.0029 e to the negative 3. So when you have e to the negative 3, right, it means 3 zeros, decimal place after the first one, and then all the digits that it gives you. Okay, and so it said 0.2%. We've got here 0.01%. So we have satisfied the claim. So it says use evidence to support the claim. So we're making this argument. We're saying we're using this information. We need to justify why we've chosen that value. So you could either communicate it in brackets alongside, or have a sentence below describing the procedure we've performed here. Using from the confidence interval, using the lowest possible value of the mean, okay, of 88.06 grams, we are 95% confident that 0.01% of packages, of oyster packages, will be below 1,000 grams. Okay. So good question there. Like it's good confidence interval one. Makes you think, like, what's the point of using these upper and lower estimates? How can we use them in calculations when we don't have a new mean or when we've changed something a little bit? So yeah, so that's it. Any questions about it? No? Very good. So I really encourage you to have a go at question 9. Okay, and then we'll talk about that on Friday.